Today we are going to start chapter 28, which is about magnetism. The science of magnetism had its origin in ancient times. It grew from the observation that certain naturally occurring stones would attract one another and would also attract small bits of one metal like iron, but not other metals such as gold or silver. So the word magnetism comes from the name of district Magnesia in Asia Minor in Turkey, and where one of these stones were found. Today, everybody uses magnetic forces. They are at the heart of electric motors, TV tubes, microwave ovens, loudspeakers, computer printers, and disk drives. The magnetism of individual atomic nuclei is used by physicians to make images of organs deep within the body. Spacecraft have measured the magnetism of the Earth and the other planets to learn about their internal structure. So, in this chapter, we begin our study of magnetism by considering the magnetic field and its effect on moving electric charge. And then later on, we will study the production of magnetic fields by electric current, and then we continue to explore the close relationship between electricity and magnetism, which are linked together under the common designation called as electromagnetism. So the most familiar aspects of magnetism are associated with permanent magnets, which attract unmagnetized objects and can also attract or repel other magnets. Compass needle is also one of its examples. But the fundamental nature of magnetism is the interaction of moving electric charges. Unlike electric forces, which act on electric charges whether they are moving or not, magnetic forces act only on moving charges. It is important to keep in mind that there are many important similarities between electric and magnetic interaction, as well as the important differences between them. Both electric and magnetic forces use the idea of a field to describe both kinds of force. In electrostatic, we study that the electric force arises in two stages. Number one, a charge produces an electric field in the space around it, and the second, charge responds to this field. Magnetic force also arises in two stages. First, a moving charge or a collection of moving charges, that is an electric current, produces a magnetic field. Next, a second current or a moving charge responds to this magnetic field and so experiences a magnetic force. So as early as the 8th century before Christ, the Greeks had discovered this piece of a mineral called magnetite or lodestone, which was an oxide of iron, and it has a property to attract a piece of iron but does not exert a measurable force on most other materials. Later, it was discovered that one piece of magnetite can either attract or repel another piece depending on their relative orientation. So, in these experiments and the ones which we will discuss, it is necessary to determine that neither of the objects carries a net electric charge, so that we can be sure these new forces cannot be of electrical origin. By the 12th century, the following experiment was known. A small needle, this one. A small needle-shaped piece of magnetite is suspended so that it can pivot about a vertical axis. Even with no other magnetite or iron nearby, the piece spontaneously rotate about its pivot and eventually come to rest with one end pointing roughly towards the Earth's north geographic pole. and we as a convention it was painted as red. And wherever this experiment was tried on Earth, the red end always point towards the north. The device which was constructed is of course a magnetic compass, which is responding to the magnetic field of the Earth, just as two pieces of magnetite exert forces on each other. So we can this outcome can be described by the same language which we use for electrical interactions, like one piece of magnetite or earth sets up a magnetic field and the other piece responds to that magnetic field, and the direction of the magnetic compass gives the direction of the horizontal component of the magnetic field of the earth. Then we can also use this magnetic compass to trace out the magnetic field of a bar magnet. Here, see, so if here one end of a bar magnet has been painted red, we paint this one as a red. So this one shows that this bar magnet is north seeking this side by convention, or simply we call this north pole of the magnet, and the opposite end is the south pole. When we bring our compass near the bar magnet, the compass rotates its needle until its direction indicates the direction of the magnetic field at that point. And there is one more experiment where the results were very surprising. If we place the magnetic compass near a current carrying wire and a steady current is flowing in that wire, the compass shows clearly the deflection, that is and if the compass the needle shows a deflection, it means that there is a magnetic field around the current carrying conductor. If we turn off the current, then there is no magnetic field and there is no deflection. So, and if we reverse the direction of the current, the compass needle points in the opposite directions. So these observations give a hint of the complex and fascinating relationship between electrical phenomena such as current in a wire and magnetic phenomena, the deflection of a compass needle. So in our next videos and in our next topics, we will discuss all these relationship and the forces which are acting and to cause the deflection of the needle. So let's move to the other video and see these things in detail.